Okay, let's get started. Welcome to the last session of the day. We're very happy to have Mitali Bafna from MIT to speak about their recent amazing result on efficient PCPs from HDX. We already heard a lot about this talk. Max gave several teasers about this talk, about this result in his talk. Mitali unfortunately could not make it. She was supposed to be here both for this week and the following week. Didn't make it for a couple of reasons, but we're happy that Mitali is consented to give the talk, even though remotely. Mitali, over to you.
Thanks so much, Prahladh. Wait, sorry, can you guys hear me? Yeah, okay. Yeah, I'm really, it was really unfortunate I couldn't make it in person. But yeah, so today I'll talk about this result on building efficient probabilistically checkable proofs from HDX. And this is joint work with Dor, Nikhil, and Zive Yun at MIT. And this builds on our recent results on direct product testing, which were also concurrently shown by Yotam Dixtein, Irit, and Alex Lubotsky. Okay, so the PCP theorem was a landmark result in computer science, which led to a systematic framework for proving hardness of approximation results. And not only this, using cryptography, the PCP theorem can be used to succinctly verify whether some large computation has been performed correctly or not. And indeed, some of these techniques are now being used in blockchains like Ethereum. So our main result is to improve the PCP constructions, which lead to better hardness of approximation results. So let's see what a PCP is. So suppose someone wants to prove a claim to you, and the claim could be anything, for instance, the Riemann hypothesis. And to do this, they give you a proof. So one way you can check this proof is to read it line by line and verify that the line you're reading follows from the previous lines. But a PCP gives you an ultra-fast way to do it. It instead tells you that you can ask the prover for an encoding of this proof, such that you, as a verifier, can toss a bunch of coins, query only a constant number of locations in this proof, and verify whether they satisfy a constraint or not, and output accept or reject. And the guarantee that the PCP gives you is that you will always accept correct proofs with probability 1, and you will accept wrong proofs with all but some small probability of error. And of course, you would have wanted this error to be just 0. You would want that you accept wrong proofs with 0 probability. But this is not possible since we are only reading constant number of locations. So ideally, what you want is to minimize the overhead of this new encoded proof and also to minimize the error. And today, it turns out that to get the implications to hardness of approximation, we need to build 2 query PCPs, where the verifier is only allowed to query 2 locations, and each location reads a constant number of bits. So therefore, today we'll only look at this setting. And note that in one query, you can't really verify anything. So this is the first non-trivial setting. So any questions? Well, okay. So now let me tell you about the size versus error trade-off in 2 query PCPs that was known earlier. So the PCP theorem showed how to get a size of polynomial in n, where n is the original length of the proof, while getting a very large error, so some error close to 1. And now one way you can reduce the error is to just make the verifier repeat itself. So verifier can toss few more coins, query more locations, and keep and check the constraint. So querying k times will give you an error of 0.99 to the k. But of course, this increases the number of queries. So if we are restricted to only 2 query PCPs, it's not even clear that you can reduce the error. And a breakthrough work of Raz showed how to do this, how to simulate this kind of repetition of the verifier, but using only 2 queries, but instead incurring a large blow up in the proof size. And then this led to a flurry of work to reduce the size of PCPs. culminating in the work of Irit, who showed how to get n polylog n size PCPs with large error. So a natural question that arose is, can we match the size of Irit's PCP with the error of Ra's PCP? So in some sense, get the best of both worlds simultaneously. So Moshkowitz-Raz made some progress in this direction. They showed how to get almost linear size PCPs and simultaneously low error, and their PCPs were based on low degree testing. On the other hand, there were also a bunch of barriers shown to extending Dinur or Raz's approaches. So we overcome these barriers by constructing PCPs that are based on high-dimensional expanders. And our result shows n polylog n PCPs with any small constant error. So the exponent in the polylog depends on the error that you want. Okay. So this immediately using the framework of hardness of approximation, this gives some immediate corollaries. So just to recall, the exponential time hypothesis says that deciding whether 3-sat is satisfiable or not requires exponential time. Using this hypothesis, you get that for all epsilon, there exists some constant that depends on epsilon, such that even approximating 3-sat with a factor that is even slightly better than random, what a random approximation algorithm would give, takes time 2 to the n by polylog n. And then you can get similar, many such results, nearly optimal results for other problems, and also for fixed parameter tractable problems. Okay, so now let me tell you about how high-dimensional expanders help to construct PCPs. So let's, I mean, this workshop is on expander graphs, so you've probably seen a lot of this. So just to recall, expander graphs are very well-connected constant degree graphs, and they have many nice properties that the complete graph has, such as the property that every small set of vertices has a lot of edges going out of it. And let's see why expander graphs are useful for PCPs. So let me mention that all the previous PCP construction before Irit's construction were based on low degree testing. And this was the first Irit's construction used a very simple methods using expander graphs. So the main idea, so the main goal in PCP construction is to take some proof which has some one error hiding in some location and convert it into a proof which has many errors, so that a verifier who just queries constant locations can catch the cheating prover. So imagine that prover wants to prove a very simple claim to you that this expander graph is too colorable. And one way it can, one proof that it can give to you is to just give you a green or blue assignment to the vertices. But let's say that this graph is actually not too colorable and there's one edge that is violated. So the idea in Dinur's construction was to instead ask for more information, ask the prover to give you two coloring of every small neighborhood, constant size neighborhood of every vertex. So at each location, it just also gives you a red or blue assignment to, let's say, 10 vertices around the vertex that you are querying. And now this erroneous edge will be part of many neighborhoods. And what a verifier will do is to sample 2 random neighborhoods and check consistency between them, that the prover has given you a consistent, the same assignment, the assignment on the intersection of the neighborhoods agrees, and also to check whether all the edges in the neighborhood are colored correctly. And the key insight was that this spectral expansion can be used to amplify the error. And repeating this procedure multiple times leads to PCPs with error 0.99. So the immediate question is, can you get down to any small constant error? For instance, can you reduce the error below half? But unfortunately, this approach cannot be used, as was observed by Bogdanov. So let me just say the reason. So the issue is that generic expander graphs look like trees locally, and trees are too colorable. So what a cheating prover can do is to give you a random assignment to every neighborhood and completely ignore the original assignment to the vertices. So now every neighborhood looks like it's too colorable. And even if a verifier tests consistency, it will only catch an error with probability half. So the issue is that expanders are locally too colorable, but globally they may or may not be. Okay, so any questions? Okay. So this suggested, like the first, the paper of Dinur and Kaufman suggested that maybe we can use high dimensional expanders to build PCPs. And let me say some reason why HDX could help to build PCPs. So again, recall that HDXs are expanding hypergraph where every edge consists of constant many vertices. And they are also sparse. So we have theta of n hyperedges, and they're supposed to sparsify or have many of the properties that are possessed by a complete hyper. And we can think of a graph based on HDX, where we replace every hyperedge with a clique. So this gives you a very well-connected graph. And the immediate advantage you get is that the neighborhoods of vertices are no longer tree-like. So let's see what it gives for the barrier. So suppose you instead had a claim that this HDX based graph is too colorable. And if you just asked a prover to give you assignment to triangles in this graph, of course, the triangles are not too colorable, so the PCP error is 0. So this graph being not too colorable is witnessed by many not too colorable triangles. Now, of course, this is kind of a stupid claim because HDXs can never be too colorable. So we want to also prove such a error reduction for other claims like 10 colorable and so on. What is the PCP error if you do this kind of a reduction? And what about more general claims that may not even be about colorability? So it looks like HDXs have stronger local to global properties. But actually you can come up with not just one Bogdanov's counterexample, but many counterexamples, even for HDX. So it's not clear that there is a definition of HDX that would imply such an error reduction for all claims. And even if we did come up with a definition, it's not clear that one can build such an HDX, just because random hypergraphs are not HDX. And we only know like 3 to 4 constructions based on algebra and topology. But it turns out that fortunately, HDXs do help to reduce the error. So PCP prover, so you can ask the prover to give you an assignment to every clique in the graph. And this we can show that the error reduces to 0.01. And this overcomes the expander barrier of Bogdanov. So let me mention the key tool that we used to do this. And the key tool was this thing called de-randomized direct product tests. which we showed in an earlier work, and it was also shown by works of Dixon, Dinur, and Lubotsky. So the main tools we used from HDX were that first we showed that this notion of co-boundary expansion that you guys might have heard of in the HDX school is actually necessary and sufficient to build these really nice objects called de-randomized direct product testers. And there are complexes, which are variants of these Chapman-Lubotsky complexes, that actually possess co-boundary expansion. So together, this implies that these de-randomized direct product tests exist, and we can use them to reduce the PCP error from 0.99 to 0.01. So any questions about this? And one thing I would like to mention is that if you see this reduction, the size of the new PCP does not blow up by much, because the number of cliques in this HDX is supposed to be linear in N. So we can reduce the error, but the size only blows up by a constant factor.
Mitali, you also
Yes.
need, are you assuming your complexes are also spectral high-dimensional expanders? And under that assumption, then co-boundary expansion is necessary and sufficient? Or you don't need spectral?
Yes. So in some sense, spectral was needed even to get to 0.99.
Yeah.
So yeah, spectral is also needed in this setting. And actually, Dinur and Kaufman use spectral HDX to get like these direct product tests in the 99% regime. And co-boundary is needed to get it in the 1% regime. Okay, any more questions?
Yes.
Can you elaborate a little bit on what you mean by these local demands? What exactly you're asking?
Yes, actually I have. We can think of everything as a 2 CSP. I didn't go to that view just because of time constraints, but think of this as this thing as having you're given a constraint satisfaction problem on the HDX. The constraint topology is fixed, but you can have arbitrary constraints on the edges. And then this constraint satisfaction problem reduces to another constraint satisfaction problem, but the soundness in the reduction is 0.01. Okay.
Mitali, one more question. So is this you already illustrated how to construct a PCP, but how do we have a initial 2 CSP which is on a HDX to begin with?
Okay, yeah, that's my next slide. So this shows that how you could take like 2 CSPs on HDX itself or like claims about HDX and reduce their error. But what if the claim is about an arbitrary graph, or like if you're given 2 CSPs on arbitrary graphs? So we reduce these arbitrary graphs to our HDX using routing networks. So now let me give you like an outline of the whole reduction. So first, you can start with 3SAT, which is either in the yes case or no case. And using the Dinur's PCP, you can reduce it to constraint satisfaction problems where yes case will go to yes case and no case will go to like value 0.99 or having error 0.99, and the size blow up is polylog n. And then the next step, we will reduce arbitrary CSP to a CSP on a HDX. And this is achieved via fault-tolerant routing algorithms for HDX. So this is the step that Prahladh asked about. Okay, questions about this? Maybe I'll talk a bit about this after this slide. Okay, and in this process, we actually blow up the alphabet to something very large, but let's ignore that. And the next step, we reduce, so now since the CSP is already on an HDX, we reduce the soundness the no value to 0.01. And this is achieved using direct product testers from complexes that have co-boundary expansion. Finally, we use standard techniques by now to reduce the alphabet from very large, like 2 to the polylog n to something constant. So this is the whole construction. Any questions about this? Oh. Okay. Prahladh, does this answer your question?
Answers the question. So, the way this step was also there in Dinur's proof, that is, she could only amplify if the original CSP was on an expander. But in in Irit's case, she could just stamp an expander on the existing CSP.
Right.
That possibly does not work over here.
Yeah, exactly. Because I mean, this HDX definition is very, like very constrained. Like you want every local name, you want spectral HDX and co-boundary expansion. So just like putting an HDX on top of your graph, as far as we know, that doesn't work.
It just ruins the expansion. Whereas if you stamp an expander on some arbitrary graph, it stays an expander.
Yeah. Okay.
Are you going to say anything about how you put a arity 2 CSP on a high dimensional expander, or is it just constant arity and you're calling it, you make it 2 later?
So we are thinking of the HDX as a graph in the whole proof. Like we are always thinking of the graph based, like the one skeleton of the HDX.
Okay. Thanks.
Just about these images. Yeah. So I'll just mention, so Prahladh, actually, how much time do I have? Like, did we start 5 minutes later? Or?
We started a couple of minutes late, so you have about 8 minutes. 8
okay.
minutes. Yeah.
Okay, so then I can mention some few details about this routing part, because that's, slightly easier than that's much easier than the like direct product testing. Okay, so let me mention this kind of very, very neat question from fault-tolerant networks. Okay, so this was actually proposed by a work by Dwork et al. In the context of distributed computing. So their question was that can we design a sparse network on n vertices and routing protocols between all pairs of vertices such that these protocols are efficient. So what I mean by routing protocol is that you want to transmit a message from one vertex to some other vertex in the graph, and you want to use only edges of the graph. So one such protocol could be just to transmit a message along a path of the graph from U to V. And we want 2 properties of these protocols. Firstly, we want efficiency, and we also want fault tolerance. So by efficiency, I mean that you should only use, like let's say, polylog n messages through the graph to transmit one message from U to V. And by fault tolerance, I mean that even if a constant fraction of the vertices behaved adversarially, like they dropped messages or changed the message they were supposed to send, even then the message transmission works out well for most of the protocols. So any questions about the model? Okay, so I will be describing this more in detail. So this was previously studied using expanders, but they couldn't get the like the best possible parameters of constant degree and efficient and constant fault tolerant protocols like that are resistant to constant fraction of faults. And our solution is to use HDX, and this also gives us the first component of the PCP result. So today, like for simplicity, just pick some permutation on the vertices, and our goal would be to design n protocols from V to pi of V. Okay, so one first attempt you can try, and this was done by many previous works, is to just use expander graphs. And between any two vertices, you have paths of length log n. So we can just use these paths to do the message transmission. So one can send a message to pi of 1 using this log n length path, and so on. And additionally, on an expander graph, you also have that each time step can use every vertex exactly once. So this immediately gives us some kind of fault tolerance. So suppose now that any 0.01 n by log n number of vertices in the graph are adversarially faulty, then only 0.01 n paths fail to transmit the message. And this is just going to be by a union bound. So at the first step, only these many vertices fail. So 0.01 n by log n paths fail due to the first step. And again, due to the second step, the same number of paths may fail, and so on. But overall, because there are only log n steps, only constant fraction of the paths fail. So the immediate question is, can you improve this 0.01 n by log n? Like, can you get tolerance against constant fraction of adversarially chosen faults? But this kind of protocols won't work because an adversary can actually choose n by log n a number of vertices and fail all the protocols. So one idea is to just add robustness to the routing procedure. So instead of passing a message along just one path, what if we did something like this, where the first vertex passes a message to small number of vertices, then this small clique of vertices passes a message to another small clique. Everything in the second clique takes a majority of all the messages it receives, and so on. And now this is more robust, since if every clique had at most half fraction faulty vertices, then the message transmission would be successful. Okay, so of course, there are no cliques on a expander. So one thing you could try is to just add cliques to your expander. And in fact, this is something that previous works in this literature did. They use this kind of expander plus clique network and like kind of overlaid many random copies of these expander plus clique network on the same number of vertices. And like every route, like every path on the expander network now corresponds to this kind of path on the cliques of this expander plus clique network. And you can use majority transmission to do the like the message transmission. And in fact, you can analyze this to show that just using Chernoff bounds to show that this network is tolerant to constant fraction of random faults. So yeah, just because if the constant fraction of vertices were faulty, but they were chosen randomly, then only very, very few of the cliques would be faulty, and the same kind of proof from before for the expander case will work out. But of course, this is not going to be tolerant to adversarial faults, because an adversary could just simulate an expander adversary and fail all the protocols by just choosing, again, 1 by log n fraction of faulty vertices. So whenever an expander adversary corrupts some vertex, you can just corrupt the corresponding clique. And the issue seems to be that these cliques are disjoint to each other. So we want some kind of overlapping cliques. And this is exactly what an HDX gives you. So again, think of the graph that we get from an HDX, which is just replacing just the one skeleton of the HDX, or like replacing every hyperedge with a clique. And Max talked about these concentration bounds that they showed, which is that if these cliques are large and even an adversary chose at most constant fraction of vertices to be faulty, then very few or you can like make the cliques large enough so that only 1 by log n cliques have greater than half fraction faulty vertices. And this is strong. This is like a same kind of result for the expander plus clique, but now it's tolerant to adversarially chosen false, which is necessary in our case. So then you can similarly set up like a clique-to-clique routing on these HDX graphs, where you choose a path over cliques and you do the message transmission using majorities. And then using the Chernoff bound of Dickstein-Hopkins, you can show that even if an adversary chose constant fraction of vertices to be faulty, then only some constant fraction of protocols fail to transmit the message. And the proof would be pretty immediate using the concentration bounds. So this almost gives us the routing, except that if you did the whole calculations, the efficiency is not what you would like not the small, and not polylog n, something larger. So we can do like a similar kind of routing protocol, but using links in the HDX. And that would give you also efficient routing protocols that are tolerant to constant fraction of faults. This uses, again, just spectral properties of the HDX. And actually doing some kind of protocol composition, you can also get constant degree networks with efficient and fault tolerant protocols. So yeah, so finally, like maybe I'll skip how this is connected to PCPs, or just say it in one line, that when a PCP was going to query some edge ij on the left, instead, this may not be an edge in the HDX graph. So you ask the prover to provide you a routing of the label from label of I to label of j. Label of I to the vertex j using the routing protocols that you have constructed. So the prover gives you much more information at every vertex, not just its own label, but also all the messages that passed through this vertex in the routing protocols. And it's pretty straightforward to show that, like if you had a PCP with error 0.99, the fault tolerance of the routing protocols also gives you a PCP with on the right hand side, but now on an HDX with error 0.99. Sorry, that any questions about this?
Very good.
Okay, and once,
No, none. Go ahead, Mitali.
Okay, so yeah, so finally, like once you have this claim about an HDX or like a 2 CSP on an HDX, now we can use the de-randomized direct product testing results from prior works to reduce the error to 0.01. This is just a recap. Thanks.
Any questions for Mitali?
In one of your slides, you mentioned some new co-boundary expanders. So why did you use these new ones? Why the old ones didn't work?
Sorry. Which were the old ones? Oh, sorry.
So you mentioned some new constructions of, yeah.
Yeah, so we used variants of the construction by Chapman and Lubotsky. Yeah. Oh, so do you mean like why did we use the variants, or was there?
But there were co-boundary, good co-boundary, but there were some other constructions before.
Actually, I think these were the first sparse constructions.
It's from 2000. Okay.
Yeah, so here we needed like vanishing of homology. Yeah.
Okay, thank you. So it's not co-systolic expansion, so co-boundary.
Yeah.
Okay.
Mitali, can you hear me now?
Yeah.
No, my question was, the second step, the agreement testing required the HDX to be both spectral and co-boundary.
Yeah.
The first step, the fault tolerant, what were the requirements? What are the requirements of the HDX? Is it just a spectral HDX, or even there you need a co-boundary X?
No, it's just spectral. And then, I mean, we use the particular properties that these LSV or Chapman-Lubowski, all of these HDX possess, like they have some symmetry in the links, but it's very few. I mean, basically just spectral expansion.
Any other questions? Okay, I have one more question. So what's needed to get to subconstant error now?
Yeah, so the exponent in the polylog is pretty bad. It will give some subconstant, but that's not going to be anything. Like it will be probably many logs.
And this is, so where is the bottleneck, in the fault tolerant or the agreement, or in both?
I think it's more in the agreement testing. Yeah.
Questions? Not, let's thank Mitali again.